Welcome PCS members and friends to our PCS IBS seminar. Today we have a pleasure of hosting Dr. Zulkaida Akbar from National Research and Innovation Agency from Indonesia. And this seminar is a part of the activities of the ICTP Asian Network on Condensed Matter, Complex Systems and Statistical Physics, which is ongoing now in its second iteration from 2023 to 26. And let me briefly introduce our speaker. So Zulkaida obtained his bachelor's from Bandung Institute of Technology in Indonesia. And then he moved to the Florida State University, where he obtained his master's in 2015 and his PhD in 2018. And then he moved to the University of Virginia, where he was a postdoctoral research associate between 2018 and 2023. And finally, last year, he moved back to Indonesia, BRIN, where he's a senior researcher. And during his work in the US, Zulkaida worked in nuclear and particle physics, and more specifically in several experiments at the Jefferson Lab and at the Fermi Lab. And there, a part of his work there, he acquired proficiency in large data analysis and machine learning. And his research interests are from before the muon topography, hadronic physics, machine learning and application to nuclear and particle physics, and also more recently, the application of machine learning to material science and in the statistical physics and complex systems. And today, Zulkaida will tell us about his recent work on unraveling opinion dynamics, insights from network science and Ising 1. Let us welcome our speaker.
Thank you very much for the opportunity to talk here. Before I give the talk, there are several things that I want to mention. First, a disclaimer. So when I was invited to give a talk, I considered two options here. First, a talk about one specific topic that I present coherently from the basic idea to the gory detail, or the option two is a talk about many topics that I present briefly with the goal to trigger the further discussion. And since I'm here until next week, until next Friday, so I choose option two. So I want to apologize in advance if I will jump from one topic to another topic. And if you have more questions, then answer after this talk. And number two is, actually, I'm an experimentalist. Specifically, I'm an experimentalist nuclear and particle physics. But I'm really happy to discuss with you many wonderful theory here, since as I discussed with Danko last night, that historically speaking, particle physics borrow many tools or inspire from the condensed matter theories, or vice versa, like the Higgs boson, viscous and spontaneous symmetry breaking that is also common in condensed matter. Or we have quasi-particle topology and many more. And there's a quote even from one Nobel Prize winner, Frank Wilczek. He said that the Higgs mechanism is, in a real case, simply superconductivity view from within the material. So with this background, there are three areas that I want to discuss today. The first area is my previous research in experimental nuclear and particle physics. Hopefully, there are challenges that probably you have insight that we are not aware. And then since I'm here to visit Tilden to talk about the machine learning, so I will talk about the machine learning application. And the third one, since this is the Institute of the Complex Science, so I have to talk about the complex science. Okay, so yeah, these are three things that I will mention briefly each topic today. So I will start with the part 0, a brief introduction about me and my research. So I've been in America for 10 years, where I spent in Florida State and University of Virginia institutionally, but I work on two accelerator here. The first one is Jefferson Laboratory. It's located in Virginia. It's a 12 giga electron volt electron beam. It also can provide photon beam, and it is dedicated to study the internal structure of the nucleon. And then I also work in Chicago, where there is a Fermi National Laboratory. It was the highest energy when it still has tevatron, but they shut down the tevatron. It still has 120 GeV proton beam to produce neutrino and other stuff. And Fermilab now consists of many experiments, from nuclear physics to dark matter and to neutrino physics. The flagship is they are building, I believe now it's 3 billion project DUN, Deep Underground Neutrino Experiment, where they shoot the neutrino beam from Chicago in Fermilab, travel under the curvature of the Earth, and detect it 800 miles away in South Dakota. So that's the Fermilab stuff. Okay, so first part, usually we experimentalist physicists always start with this plot here to show that we know next to nothing about our universe. So according to astronomers or cosmologists, the one that we know, that we call it visible universe, is only 5%. The 95% that we don't know consists of dark energy, 70%, which is responsible for accelerating, expanding universe, like anti-gravity thing. And 25% of the universe consists of dark matter. Both are dark because we don't know, we don't understand the nature yet until today.
Sorry, how can you tell apart that there's energy and matter? The dark ones.
Okay. So the historically for the dark matter, people do survey on many galaxies, and they observe that the rotating speed of the star is not as it is if there is visible mass there. It's more, the speed is more as if they have more mass in that area. So we don't know what is it. Let's call it dark matter. Yeah, if the dark energy with the Hubble telescope and no James Webb, the universe is just expanding, and we just call it dark energy. Just a label for something that we don't know. Okay, but if we go to the 5% that we know, it's even we don't understand the 5%, we know that almost 100% of the 5% that we know is concentrated in nucleon. If we look into the atom here, I think we understand really well the quantum in the atom level. For example, we know that the hydrogen mass here, like 938 MeV, consists of proton mass plus electron mass and plus electromagnetic interaction. Okay, that's a normal number. Okay, let's go to the proton mass. We learned that nucleon, a proton, consists of 3 valence quarks. But if we do the summation of the mass, the 3 quark mass only constitute about 1% of the total mass of the proton. Where is the 99% of the total proton mass come from? It's come from the strong interaction between quark and gluon and so on. So not only the origin of the nucleon mass, but other nucleon property also we are not fully understood. I mean, in nuclear physics and particle physics, we have the term like proton spin crisis. Okay, we know the proton spin is 1/2, but where did it comes from? Okay, how much is the contribution from the spin from the quark, from the gluon, from the orbital angular momentum of the quark and gluon and so on. And even there is also a term called proton radius puzzle. Different experiment measure the same proton radius with different technique, they come out with different number. So it's very confusing in this field. That's why I'm planning to escape. Okay, so briefly I will, when I was in Fermilab, my experiment is to address this proton spin crisis. The experiment is called a spin quest. The idea of the experiment is simple. We have polarized proton target. We shoot with 120 GeV proton beam. The beam will carry a quark. The target will carry anti-quark. The quark and anti-quark will meet. They will annihilate and become photon. And then the photon will make a pair production between the lepton, muon plus and muon minus. And then we will detect the muon. The idea is if there is a C-quark orbital angular momentum, they will manifest in left-right asymmetry in the decay product of the muon. Well, we just starting the commissioning run right now, so we will not hear the result whether there is orbital angular momentum from C-quark or not, probably until next year or until next 2 years. So in the last, yes?
I ask a naive question, but as far as I heard, some lattice calculation and quantum chromodynamics, they can reproduce actual spin of proton, for example, or neutron.
Correct. So lattice calculation essentially put a number quite big. I think it's like 30% is from the orbital angular momentum. But well, our experiment is want to prove it.
Okay.
Yeah, it's experiment. Okay, so we will wait maybe next 2 years. Hopefully, we will have a statement from this experiment. Okay, and then the last thing, other than nuclear structure, I was also studied about the baryon spectroscopy. So theories make a model. What I show here is the simplest model called constituent quark model. Okay, if we know that inside the nucleon there are 3 valence quark, so let's put 3 valence quark here, and then let's make a Hamiltonian where there are 2 spring-like potential connecting the quark. Let's call it rho and lambda, and they can have like excitation, right? They can rotate, they can vibrate, and based on the excitation of this spring-like potential, there should be a spectrum of resonance. People predicted it, and lattice QC also predicted. And the thing is, we don't see it in the experiment. This problem is called missing nucleon resonance. So another problem here, and that's what I did in Jefferson lab. We did spectroscopy. Well, in analogy with atomic spectroscopy, usually in the atomic spectroscopy, we excite the atom, and then we detect the photon that is produced when the atom is transitioned to the more stable state, and then we map the spectrum. That's how spectroscopy works in material science. But the lucky thing is, like this one, hydrogen spectrum, the spectrum is sharp and clearly identified. But that's not what happened when we do nucleon or proton spectroscopy. What we did is we excite the nucleon by shooting it with high energy photon beam, and then the nucleon will excite into nucleon resonance, very short-lived, and then it will decay. It will go back to the normal proton and decay to some other particle. Well, this is the spectrum that looks like. It's very overlapping. Even in one broad peak, there can be 1, 2, 3, 4, 5 resonance. So peak hunting doesn't work in this area. So what we normally did is use, we call it a partial wave analysis. Well, partial wave analysis is simply a technique to find what happened in between. So usually a theorist, okay, so for example, what I did is I find a final state of P and omega. Omega is a meson, 700 MeV, and there must be something resonance here. So the theorists usually calculate a lot of Feynman diagram by putting many resonance and then fit to the observable and find the process is iterative until they find a set of resonance that give best fit to the data. That's how it works, iterative. Okay, let's put this resonance, and so on. Like for example, okay, let's put this resonance, let's put the resonance. We are okay, we are running out of Greek symbols, so we're just naming this particle as N200. This is like the mass. This is like the quantum number, something like that. And this is what I did. One of my publication. It's only a wiggle curve, and then the partial wave analysis group doing that tedious calculation with the whole set of resonance, and then fit my measurement until they. I think this is already good fit, and this is the set of resonance. Yes.
So when you put all these resonances and these kind of things, generally are you only considering tree-level diagrams, or are you also kept considering group directions? Because all your earlier diagrams were just tree-level diagrams.
What I understand is only tree-level diagram. So they are the group in the one that doing this is a theory group in Bonn, Gachina. So it's like collaboration from Bonn and in Russia. Gachina, I think so. It's a city, Russia. So oh, you're from Gachina. Yeah. So we are collaborating with the Bonn Gachina group. The idea, okay, here's my data. Okay, you do the fit, something like that. And then they told me, okay, this is the fit, but yeah, I believe it's only tree-level diagram because it's a lot complicated.
I also have a question about this missing resonances. You said that you use laser to excite nuclear, but is there a proof that you can excite all the resonances using this laser pump? Okay,
so the whole business of missing baryon resonance is started use pion beam essentially. It started in 70s. They use a pion beam, and they use a pion beam, and they do it, I don't know, 20, 30 years, and then, hey, half of the rest predicted resonance is still missing. So, okay, let's build JLab, and we try with the photon beam. That's the idea. So the photon, the laser, or you call the laser, it start after 20 or 30 years using pion beam, and they are still missing. Right now, they are still missing, even after 20 years using the photon beam in Jefferson Lab. Okay. Well, in this part, I will close what I learned so far as experimental nuclear and particle physics is we know next to nothing about our universe. There is always surprise. So this is one of our paper that published in Nature 2022, where we have another surprise. We measure like, it's called electromagnetic polarizability. And what we found in the data is different with any theoretical prediction that is exists. So more surprise, I would say in terms of engineering, it's miracle, like a JLab. They can deliver very fine beams simultaneously to 4 holes with different current, very, very precise. But in terms of theory, I think we stuck. Okay, and then the other thing is there are many hardware and instrumental technique that I learned from dynamic nuclear polarization, NMR, cryogenic, software and data analysis, and then machine learning. Yes?
Is this G-2? No.
No, G-2 is Fermilab.
Okay, but when you were measuring electromagnetic structure, what else were you measuring?
For this one, we use, we call it VCS, virtual compound scattering. So it still use the photon beam, but in very forward angle. And then we probe as a function of Q square, essentially. Yeah, the scale. The J-2 also published some interesting result from Fermilab, like, I don't know, 2 years ago, I think.
But G-2 would also be measuring something about electromagnetic structure.
In my understanding, yes. What G-2 people do, what G-2 people did is calculating more and more ion diagrams to make it more and more precise, essentially. Yeah.
What kind of theoretical predictions are these? What models are they based?
For this one here?
Yeah.
Okay, so, well, I try to answer from what I remember. In general, the most common technique right now is lattice usage in general.
Okay.
In general, and there are some like Dyson-Singer equation, something like that, if I remember correctly. Approach. Yeah. Well, I'm sorry, I couldn't answer it.
I mean, we have this theoretical nuclear physics group in Darmstadt. So they did also nuclear structure computations.
I see.
That's what they are doing. Therefore, I'm asking.
Yeah. So the one that we see is, okay, some model, all model essentially like this, but we found a bump that is unexplained.
Okay.
Yeah. Okay, so since one of the things that I learned is machine learning, so we move to the next part 2, which is why I come here to discuss with Dylan and colleague. And so when I come to Indonesia, okay, I think I'm not going to America again. It's too far away, with the paperwork is hell and something like that. Let's find something that I can apply in Indonesia but I'm going to join CERN this year. One of the things is machine learning. So, and I talk to colleague, hey, what can I do with machine learning to help you analyze your data? Okay, machine learning right now is very, very hype, very buzzword. Sometimes it's become a mistake, something like that. So I will call it, the part 2 is demystifying machine learning, which is a simple word. In a simple word, although not 100% correct, machine learning is just a universal approximator. There's a mathematical theory about it. It can approximate any function that can be used for prediction, classification, or find a pattern. One of the easy example is how we teach machine learning to recognize number, handwritten number. Essentially, it's just like when we teach the kid how about the number. We don't give the computer a definition. For example, okay, number 7 consists of 2 straight lines with the angle of 30 degrees, for example. We just saw, here's number 7, here's number 8, here's number 1. 1,000 people, so 1,000 example, and let the kids learn, and let the computer learn. Yeah. One thing that I described is called supervised. So essentially, if traditional programming, we give the data, we give the program. Okay, this is, if you find 2 lines and the angle is 30 degrees, that's number 7. But in machine learning, we give the data and we give the output label. We train with the example. That's the supervised learning. It can do for classification, regression, and so on. And then I talked to my colleague from the neighbor Center of Photonics, and then he said, hi, I have a data from laser-induced breakdown spectroscopy. So this is a spectroscopy to characterize material. The idea is shooting the sample with a laser, short laser pulse to create a microplasma in the sample surface. And then when the sample is cooling down, they will emit a photon. And here's what it looks like, the spectrum. Okay. The advantage is it fast. The sample preparation is easy. But the disadvantage is low accuracy and poor reproducibility. Sometimes it's calibration problem. Different people, different setup, it has different spectra. But hey, maybe we can help with the machine learning. Like 1,000 people must have 1,000 different handwritten, right? But still, the computer still can recognize the number 1 to 9. And here's the sample. We try. Indonesia is, I think Indonesia is number 1 or number 2 coffee producer in the world. So my friend just, okay, let's take a coffee, 2 coffee. First 2, one is Arabica and one is Robusta. So he played, and we took, he played 39 samples of Arabica coffee and 9 samples of Robusta coffee with this kind of spectrum. So this is the Arabica number 38, Arabica 29, Robusta sample number 8, and Robusta sample number 6. In my eyes, I cannot differentiate this one. The trained barista, they can distinguish with the smell. But that's a trained barista. Okay, so I have a money student, and okay, let's play with this data and see if we can, first step, we can classify whether this is Robusta or Arabica. Probably the next level, we can Robusta from Java, Arabica from Aceh, and so on. But let's start with a very simple one. Okay, I'll give this task to my student. And my students start with a very traditional machine learning, neural network. This is very traditional machine learning. The idea is we have the input layer, we have the hidden layer, and we have the output layer, just for classifying. So what is the input? Well, the input is every intensity in every frequency. So that's quite a lot. It's 24,000 of input neuron corresponding of the intensity for every frequency. And then my student play with 3 hidden layer with this is some detail, ReLU activation function, and then the output neuron is 2 corresponding to the probability of this being Arabica or Robusta. And there's a challenge here. The challenge is when we talk about the neural network, machine learning, people usually say, we need thousands for training, right? This is what we usually heard. What we have is only 48. It's not even 100. And it's imbalance 139, 19. Luckily, we found some technique called SMOTE, synthetic minority oversampling technique. That's good for imbalanced data set. They usually create a replica to make it balanced, like some sort of generative adversary network. With this thing, my student got the accuracy of 94%. So we are still, well, it seems that 95% is psychologically good number. So we still want to improve 1 or 2% before we publish it.
You're adding some additional noise. Is it possible to verify the what percent of this time, what percent?
Oh, so we still want to fine tuning the hyperparameter.
But you're adding the additional small noise on
Like more layer?
Yeah.
More layer?
No, original data.
Oh, the original data. So no, we found we tried with this data, and what this synthetic minority oversampling technique did is like they creating more data, but it's automatic. I mean, to be honest, it's like a black box. In Python, you can just call it the SMOTE library. They will automatically create an additional data set, like a synthetic data, to make it more balanced.
I question the related some classification problems. So sometimes noise, small noise, human can easily understand the noise pattern, but the machine sometimes give the very wrong result because of some high-tried noise.
Okay. Well, I understand the problem. That's why I'm not sure whether the additional technique will fully answer your concerns, but we did a K-poll for cross-validation. So we did several iterations with different sampling of training set, validation set, and testing set to make sure that is not overfitting, not underfitting. Yeah, that's one of the things that might answer part of your concern. Yeah, K-poll cross-validation technique.
Maybe a related question. So this oversampling, how many samples do you then obtain?
Oh, for this SMOTE?
Yes.
Yeah, that's a good question. I have to ask my student. So I will provide the answer tomorrow when we discuss it. Okay, well, that's a luxury of have students. Okay, so yeah, I'm sorry. I will need to ask my student what this one is. Okay, now number 2 is the muon tomography. So this is the technique that we borrow from particle physics. I mean, we're detecting muons in 60 essentially. And this made a big news like 5 years ago or 7 years ago, when the muon tomography found a hidden chamber in a pyramid. So what they do essentially is very simple in terms of technique. So we know that we are granted by cosmic ray muon, right? It's a free source, high energy. 3 GeV is the average. So what people do, and we know that when the muon enter high density object, it will scatter. So the principle is simple. We put 2 stations on the top and on the bottom before the muon scatter by high density object, and after the muon scatter by density object, and from the scatter angle, you can reconstruct the object between these 2 stations of the muon. That's the idea. It's called muon scattering. Or we can do also muon absorption. That's what they did when they found the hidden chamber in Pyramida. So they just rolling around the muon detector, and they compare the intensity of the muon in different technique. They put here, they put here, they put here. By comparing different detected muon in different area, they can reconstruct what is inside. Okay, so that's the muon tomography technique. And people use it after that invention. People use it in many areas. They can use it to probe the nuclear reactor, or even in here, in Central of Underground Physics, I believe the building, that area, they use it for underground imaging in the tunnel. And in Italy, in France, they use it for volcanology, real-time volcanology activities. Okay, now the challenge is, so far, they use muon tomography for probing big and dense objects. Can we use muon tomography to probe small and less dense objects? That's a challenge. And we found something that if it works, it will be really great. So we want to use muon tomography to probe oil scale in the pipeline. So scale means the deposit, right? So pipeline transporting oil, and it become solidified. And this is a big problem in oil and gas business. Okay, if we can do that, it's small object, of course, compared to hidden chamber in Pyramida, and it's oil, so it's less dense than solid rock. Although it's already solidified, but it's less dense. Okay, and then first we want to see in the simulation. Okay, and in particle physics, we have a common software called GN4. We build in the simulation, we put an object, and then we try if we can reconstruct. We start with, okay, put any object that is dense. Like, for example, we put solid iron. And as we expected, we can reconstruct the image. But when we put the oil scale, as we expected, we cannot see with normal reconstruction method. So, okay, we cannot do that, but let's think what we can do. We still want to do this because this is a big problem in oil and gas industry. And normally what people do is visual inspection. They need to stop the production, which is very costly. Or they use a lot of advanced techniques such X-ray and so on, which is also costly. Muon tomography, if this is successful, because the X-ray is free, is a cheap inspection method, and it can be disruption in the market. And then, hey, the oil company doesn't need a full imaging. What they need is only the thickness of the deposit, right? So probably it's okay if we cannot make a full imaging, only probing the what's called the thickness of the oil deposit. Probably it's okay. So okay, let's try a machine learning method, and this is also work of my student. He tried k-nearest neighbor. So his idea is, okay, we generating a sphere simulation, the angle distribution for every thickness of the oil scale. So from no oil scale, 1 centimeter, 2 centimeter, and many, many more. And then we compare the distribution with to the reference. So one of the distribution pipeline with clean pipe with no oil scale, we use this as the reference, and we use the other distribution, oil pipe with scale, as a test distribution. And then we compare those two distributions using Kolmogorov-Smirnov test. This is a simple statistical test to compare two distributions to check if two samples come from the same distribution or not, by comparing the cumulative probability distribution and see the maximum distance. But the idea is from testing with the reference using Kolmogorov-Smirnov test, they can output a number. Yeah, right. Some people like p-value, some people like d, but it's the same number essentially. Those numbers that we use to train the machine learning with KNN, K nearest neighbor for regression. This is just illustration, KNN for regression illustration. This is lazy machine learning because it's lazy. They don't do anything essentially. Maybe even it's not machine learning. So for example, if I have 11 data sets, height, age, and weight, and one is missing weight, how can I predict the number of this weight based on the other data set? And then we put them in n-dimensional space. This case is only two-dimensional, age and height, and height. And then for the thing that we want to sample, we just measure the Euclidean distance for a number of k neighbor. For example, 10, 20. So we measure the distance, we choose the 20 nearest neighbor, and then we just find the average. So that's it. So it's not really training essentially, but it's sometimes if the number is huge, measuring the distance, computational, it can be expensive. So here's that, but the one that the train is the p-value from the Kolmogorov-Smirnov test, and we have quite a good sample. Like for example, the real scale is 10.2, we get 10.5, sometimes it's off 10.1, the prediction is 8, and then we quantify with the pool distribution. The pool distribution is just the prediction minus the truth value of the thickness, and then make a distribution and find the sigma. That's where define the resolution, and the resolution right now is 2.7 centimeter for the accuracy or the resolution. This is not good enough because 2 centimeter resolution may be good enough for the industry. But of course, there will be resolution from the instrumental, right? They're always like a cable loose and so on. So we reserve 2 centimeter for the instrumental resolution. That's why for the algorithm, I want to be perfect. So yeah, we still improving this one here. Okay, so since I'm running out of time, I haven't talked the third part. Just one example, again, of the application machine learning is the Raman spectroscopy. This is similar with the previous spectroscopy, but this is used inelastic photon scattering in the material. The scattered photon gain or loss of energy depend on the material structure. And this is also the work of my other student, and we collect human teeth spectra. Male, female, and some of them are smoker, just for the curiosity. I don't know why my friend picked that object. And we see here that the spectrum is, of course, we cannot differentiate, classify with eyes, right? So, and it's also imbalanced, 8 male, 18 male, 31 female. It's even around 50 sample. In the picture above, P is female, L is male, and the number is the age. So for example, this blue one is female, 44-year-old. Everything looks the same to me. And the challenge that I give to my student is, let's see if the machine learning can first, the easiest thing, classify male or female. And number 2, we have 4 smoker, detect see if the machine learning can detect the smoker. Number 3 is predicting the age. With this 50 sample, 49 sample.
How many samples do you give?
Oh.
This is medical data, is not easy to get.
Yes.
So, but the small data is already from PowerPoint.
Yes, that's a challenge. It's not as easy as take the coffee as human did.
Yeah.
Well, yeah, this is what we have right now, what my friend from the Center of Photonics have. So we see. But yes, it's not really easy to get. We are trying to get more data by contacting some of the dentist faculty in university. It's the same. The neuron input is the intensity of the its frequency. And for the gender classification, it's 100% accuracy for the gender classification. Yes.
Why didn't you use the SPOTE in this?
Not applied. So first,
Here also there is an imbalance.
imbalance. Correct. Yeah. Well, the same thing. I have to ask my student why he didn't apply it. But I think this is the best one. Maybe he tried to apply, but then the result is the accuracy is less than 100%. Yeah. So for now, that is the best architecture. Because for the gender classification,
Imbalance here is not as large as the other.
yeah, that's probably the reason why my student didn't do that.
But you need to synthetically increase the number of data.
Well, there is no recipe that we have like 50-50 or 60-40. Yeah. So we cannot make sure that if it's 40-60, is it better than 50-50 or not? I mean, there is many factors involved here. But I think 18 and 31 is not as imbalanced as the previous one.
That's why I'm curious why this Raman data is related with the condition of truth, right?
Human truth, yeah.
Yeah. But why that is related with the what? The female why gender is important? That's
Why gender is important?
Gender is why female and male is why is it different?
Oh,
We teach any reason why the relation
why
and this condition of this is
why is it different? Yeah, I mean, machine learning can see if woman, a male and female are different, and your question is why is it different in terms of the spectra?
but the sample is only is 80, less than 100 or 1,000. How to
Okay,
convince this
yeah.
relation is a real relation?
Okay, so that's a good concern. I mean, in the machine learning, we always okay. So here's the thing: machine learning, if we can control machine learning, it can be overfit. Even it can fit the elephant. People saying that. So we have to convince people that it is a true fitting, not overfit, not underfit. There are some regularization technique to do that. Like the most common one is monitoring the training loss and then the validation loss. That's number one. Number two is the cross validation. We sampling every iteration. We sampling differently. Which data become training, which data become validation loss. And number three is like a dropout method. That's also people know the dropout method is also a method that can be regularization to overcome overfitting. That's three things that it's in my head right now. I have no further idea how to convince people beyond those three methods that this is a correct fitting, not overfit and not underfit, with this sample. Okay, so well, as I expect, so the other thing is I just mentioned here, I also work in neon spectroscopy with collaborator from Riken, but unfortunately, they are kind of, yeah, they don't want to show the data, so I cannot show here before published, but it's muon spectroscopy. But we play from simple neural network to dimensional reduction technique, like principal component analysis, autoencoder, and soft organizing map. That's the plan. But this can also, I am also curious right now to see which spectrum here, which part of the spectrum that best make differentiation between male and female, for example, or Robusta and Arabica. And I'm so curious to see it with the principle of with dimensional reduction technique to see if they can make difference. Okay, I have 10 minutes probably or 15 minutes for the third part. The third part of my talk is now we move to the complex system, unraveling opinion dynamic insight from network science and Ising model. So this is a marriage between social phenomena, network science, and phase transition. So the first two is my job, and the third one here is my hobby, essentially. So it starts with my hobby. I'm always interested to learn about social change. So for example, there is a famous book called Tipping Point by Malcolm Gladwell, that there is a phenomena, social phenomena, that a sudden and massive change in society, like the steep drop crime rate in New York, the sudden rise of popularity for a particular fashion and something. We see that, right? Sudden and massive change in society, and we call it a tipping point. And even there is an empirical social law that the critical mass is 25%. If 25% of the population adopt new thing, idea, technology, opinion, then eventually the majority of the society will adopt it. This is social empirical value. So yeah, we say why Google Plus failed, right? We heard Google Plus, and I don't know, 1 year, and then after that, but Twitter is booming, something like that. Okay, so it starts with my hobby. And then, yeah, I mentioned Google Plus, and then I just read how, for example, government apply photovoltaic solar cell to move electric car. And we see what it's called a technological adoption curve. For some technology, it's also like a phase transition. Oh, suddenly everybody use electric vehicle. Suddenly everybody make Instagram account, for example. And this is related to politics. There is a nice paper. It's about where should the social movement start, core or peripheral. There is a paper that looked in the political movement in Arab Spring. And the nice thing that they found is who is responsible for protest mobilization. Model of disease and information diffusion suggests that those central social network in the core usually is the one that responsible. The one who has more network usually is the one that responsible to initiate a movement. But that's not the case in the Arab Spring movement. By surveying the Twitter, the movement starts in the peripheral of the network, not in the city, for example. And then I also interested, there is a new farming technique adoption. This is still technological adoption in Malawi, where they survey the network and they choose people in the network based on the network survey. They design a strategy to introduce a new farming technique. Okay, so this is my hobby. I read it. And then it looks interesting first because the curve is like phase transition curve. Physicists have phase transition since, I don't know, 50 years ago. We have the tools, we have the model. And I look in the social journal, what the model that they have usually is a differential equation that couldn't answer and explain the phenomena. So, okay, this looks interesting. If we can have a physics model or physics borrow model that can answer some phenomena that I mentioned before with the network science. Okay, so let's start with a very simple one, with the opinion dynamic. Try to understand if and how majority opinion are formed. Let's try with that one before we go to the more complicated thing like political movement or technology adoption or something. And the opinion here is simply being binary, yes or no, like a spin state, up and down. Because I'm newcomer in this area, so it's normal. I choose the easiest one, me and my friend. Okay, so Ising model, everybody know Ising model. So first, the thing is we have to identify the social phenomena to be translated into mathematical equation, of course. And then the social phenomena that we observe is number one, this is called majority role in opinion dynamics. Common people tend to follow the majority, right? Conformists. I think more than 50% people are followers. Of course, if everybody is leader, then the world will be chaotic. But it is proven from sociologists that a few people show non-conformity behavior. So this is the language from sociology. And there are two kinds of non-conformity behavior. First, independence, or two, anti-conformity. So the independence people is independent. They don't care about what people saying. But there is also anti-conformity. There's a group of people that they care with what people say, but if majority of people say plus, then he will say minus. He just want to against everybody in every opinion. So this is anti-conformity. Okay, and then we go to the, I inspired by Ising model. Each person is represented as a spin with a spin state up or spin down. And then we make an algorithm. This is just submitted, not yet published. This is the preprint, phase transition and universality in the majority role model with social noise and various network topology. So the idea is simple essentially. Okay, we prepare, initially we prepare randomly a state, spin state, and then we draw a random number if with some probability that he is independence or anti-conformity. But if the random number falls to the area that he is conformist, then he will see the neighbor in the network, and he just follow what is the majority in the network. So that's how we translate the majority rule to the spin state. Well, the idea is, okay, the Ising model usually is in the lattice, but that's not how real world works, right? So now we turn into the network science to find what is the real world network looks like. And that's how we go to the network science. Okay, I have 5 minutes, so I will go quickly. The network science is it's an old knowledge, but it's getting popular after August 2003 blackout in America, in North America. So 2 falling trees in Ohio suddenly create a cascading effect that makes almost 50 million people without power for a few days. So it's a cascading network. This happened in 2002. And this blackout is just one example among many cascading phenomena, like a financial crisis or credit crisis. And that's how people start to learn seriously about network structure. People now want to understand the structure of the network, the dynamical process within the network, and to design the network that are robust. That's how it starts. People interest in network science. And there is many networks. And the first systemic study of network structure were done by Paul Erdos and Erdos-Renyi. I think this is very respectable Hungarian mathematician, I believe. He's the one, he start with a very simple one. Let's construct a random network. Start with n isolated node. Oh yeah, the language is borrowed from the graph theory. And that's like a notepad, it generate a random number and so on, but it's generate a random network. And then they study the property of the random network. We call it Erdos-Renyi network. And one of the property is the probability of connectivity. What is the average, what is the number of the neighbor, the connectivity, the K here. And then I think it's follow Poisson distribution for the random network. And we see it's not represent the real network. So this is the internet network, this is the science collaboration network, and this is the protein network. All network in real life, they have a tail. So there's always a few people or few nodes that has many nodes. Like, I don't know, maybe we call it influencer node. So, okay, and this is just example of the connectivity degree from internet network, internet actor network in Hollywood, and protein, and so on. Okay, so if the world is really a random network, then everybody will have close friends between 968 and 1032, which is not correct, right? That's why this model then improved by Barabasi and Albert. He noticed two things here. The network always grow over time, right? Like the population grow. So he created the network that each time step, the size is growing. And then there is called preferential attachment. In real network, new nodes tend to link to the more connected network. That's normal, right? Hi, I'm newcomer here. I want to have close connection with the famous people in this field. This is how real world works. And with this algorithm by Barabasi-Albert, then we see here, it's more start to really mimic the real world. There is another network also. It's called Watts-Strogatz network. So this is small world network essentially. Well, this is the algorithm. This can replicate the small world property of the network. So in our paper, we apply the majority rule model with non-conformity behavior to regular network as well as the network that I mentioned. And I'm almost in the last slide. Some result here. We see a phase transition. The y-axis is the magnetization M. I mean, M equal 1 means that everybody confirm, make consensus. 0.5, no. And what we can see if from here, for example, if in the society there is 30% non-conformist, then those society never achieve consensus. That's one conclusion essentially, which is makes sense, right? But if the society is less than that percent, the one that we have independence or non-conformist, then at some point it can achieve consensus. And then we also yes.
Can I ask in network structure, the only important thing is the network structures. How can you realize your 4 rules? I mean, in first part you talked about the 4 rules for conformity.
Yes.
And so network structure is just a link between the vortex.
Correct.
Yeah.
So essentially, the original, usually people apply the rule to the lattice-like structure, right? Like 3D or 2D.
Yeah. My question is how can apply this rule to the structure, lattice structure?
Oh,
what's the coupling between them?
Yes. So for example, first we use like a Monte Carlo simulation, right? Every step we pick randomly one in the network, and we see the neighbor, how many nodes that connected to that particular percent, and see the majority of the one.
That means the first model you only for 4 neighbors, 4 site has 4 neighbors.
Yeah. So
That's
we,
model.
yeah, we try first the complete graph where everybody connect to everybody, and then we try regular network, which is 2D or 3D, and then we try this heterogeneous network, where everybody not connected to everybody, but following this Barabasi or Stats network.
I confused in spin model. Is it available?
In spin model.
Yeah, we talked about the spin model. No, Ising model.
Oh, well, that's why I don't use Ising model anymore, but it's inspired Ising model.
Yeah, I understand.
Yeah, inspired Ising model. So we just use the logic of Ising, where a spin is influenced by its neighbor, essentially. And what is the neighbor structure like? We use this network science structure.
Yeah, thank you.
Yeah.
So, sorry, so the network science tells you how in the next step you will update the behavior of the nodes, right?
The behavior is this sorry. Yeah, this behavior is we are the one that define. The network science, we use software called Network X. They have a beautiful tools to create the network structure.
So the connections are like random. I mean, the number of edges, for example, like the degree of each nodes, are they like random or are they uniform, or like you are varying it so that you know like how many neighbors each node has?
Yeah. So essentially, it's random, but following some probability that defined by the network model, whether it's Erdos-Renyi or Albert Barabasi. It's always random, of course, but the probability is defined by that particular network structure model. Yeah. When you can apply the Network X, it's very cool software. Yes.
So independent probability means this is rejection rate or
the rejection.
what is the meaning of independent probability?
Oh,
this is a kind of rejection rate or if reject P is infinity, that is only decision is random.
okay. So, yes. So, yeah, I understand. So, there's a P here, right? P is like a probability. Yeah. So, here's the thing. So, first, for example, in one iteration, randomly, I pick this node, for example. And then I throw a random number from 0 to 1, where we define, for example, if we say the probability of anticonformist, for example, is 0.3.
You standard method progress so update this P is transfer.
Yeah. So for every P, we do many Monte Carlo simulation. So first, for example, for P 0.3, okay, we choose one particular node, we throw a random number. If it's less than 0.3, then it's anticonformist. If it's anticonformist, then we will look into all of the neighbor of these nodes. If the majority of the neighbors say up, because he's anticonformist, then down, something like that. And then we try 0.35, we try 0.4. So every probability we try many iterations to see what is the stability, whether it is consensus or not. Okay, and then my friend, which is theorist, also doing a fit, and he found that it's aligned with the Ising model universality class, but I'm just started learning about this, so I cannot answer if you ask question about this one. I know.
So that will also depend on what he was asking, that how these nodes are connecting.
Yes.
So you have to, at the end of the day, you have to average over all these types of connections, or
Yes.
how do you make a general statement that if the anti-conformity probability is 30%, then
That's very good question. Yes. So if you, the short answer is yes, you're correct. So every probability, we do many steps and we iterate that many times and averaging. I think in that paper we use the term realization, something like that.
Okay.
It means that we are averaging because it is random.
Okay.
So it's very simple idea, but it just takes time to just reiterate again. That's a good thing to have students. Okay, so that concludes my talk. In summary, in this talk, I share my previous research on nuclear and particle physics, machine learning application in material science, and then the opinion dynamic based on network science and inspired by the Ising model. Hopefully, this could be a starter for a further discussion. I will be here until by the end of next week. And hopefully, if we can come up with some idea of the project, I have many students that are good at coding. So for the heavy lifting stuff for the future collaborators. Okay, thank you.
Thank you, Zulkaida, for this nice talk. And yes.
Quick question. So when you in network X, you essentially say that this is a Erdos-Renyi network, or something like this. So once you define the rule, then it chooses this connections, how these points are connected.
Yes.
And then you generate realizations, and then for each realization you keep doing this metropolis algorithm, and then you from there. Okay.
It's like for Ising, you would do always you would start with a random configuration and do your evolutions.
Easy because it's e to the minus beta h, so you know the distribution.
Yes, but I mean also the connectivity is always the same, right?
Yeah.
But here your network will change, so you have to do one run with one
So
network,
two things.
and then you have to sample over network,
and then there is connectivity.
Yes.
So you have to average over two of them.
You have to average over, yes.
Okay.
And all of these connectivities are they're non-weighted graphs or they're weighted graphs?
No, their weight depends on what network it is, whether it is Erdos-Renyi, I think, which is completely random, or is it Barabasi-Albert?
I think there is order. That weight means every link has the 1 or 0.
It's just binomial.
Order is different. I think weight is link give the information 1 or 0. Yes. If there is weight,
you can look at it like
so it's just connected or not connected, essentially.
The next step that you could do in principle is to also change the weight of the connection, but usually it's 1 or 0.
Or make direction, so it's like a graph, directed or undirected network. That could be the next cool stuff that we can apply.
Do you have any idea for directed
graph?
Yeah, in that case, it's very different from the bidirectional.
Not yet, but I'm interested to look into the information flow because it's directed, right? For the mass media and so on.
So by directed, you mean the opinion of A will influence the opinion of B, but not
So
if you calculate it.
I mean, if you are trying to model some political something, then whether it be so there are some influential nodes who have directed outwards.
There is a good insight because there is a paper that started it model mass media as an external influence and it model mass media as a magnetic field. But the paper is applied on regular lattice 3D. I mean, if we already have the networks like Barabasi-Albert that kind of mimic real world, and we can improve it to the directed for the information flow, then it can more and more realistic social situation. So yeah, the insight is really good, but we don't know yet technically to fine tuning the network next.
every positive cell strongly biased, polarized.
Yeah.
That means more state is not the ferromagnetic, more close the phase separated state.
Yeah. So that's also something that probably we can prove, like the polarization, right? It happened anywhere. I was in US for 10 years, so I know how the polarization looks like in the country. Yes, you're right. I mean, it's good if we can prove in the simulations how polarization can form, what kind of interaction. Because there is one funny experiment. Okay, so you are Democrat, you are Republican. The experiment is people thinking like this. Thinking like negotiation when you are selling the horse, okay? The seller try to put this number, the buyer try to put this number. Hopefully, they can reach the middle point. So they isolate one Republican. Okay, in 1 month, you read CNN. And they isolate Democrat. Okay, in 1 month, you read Fox News. What happened is not this extreme, this and extreme, this, they meet in a middle point, but they are more extreme after that kind of insight in the social situation that I want to learn and have a model. But with this baby step, hopefully it can more and more involve to a real situation that is complex.
Do we have Domin?
Is it somehow related to game of life? Because also game of life here is like inner pixel, which is affected by the outer pixels.
Game of life. Cellular automata. Yes.
Right.
Yes. I believe the cellular automata is yes. So cellular automata, what I understand is how to understand emerging phenomena from the microscopic interaction, right? So, for example, how the bird can migrate like with this V shape, but no leader, essentially no leader. They just following, they just respond to the neighbor. So the answer is yes, cellular automata. The idea is the same as cellular automata.
Okay.
Okay. Seems there are no further questions, so let us thank Zulkaida again.
Yes. Thank you. Yeah, I will be here until Friday next week. So in this